Okay, let's look at this Unit 9 practice test. Okay, so the melting points of the molecular compounds HX, HY, and HZ are shown. Okay, which of these elements has the greatest electronegativity? Well, the idea, H's are all the same, so the more electronegative, the more polar these molecules are going to be, and the more polar those molecules are going to be, the stronger those forces in between them. So if we have a plus and a minus and a plus and a minus, there's going to be attraction. So the more polar the bond, the greater the attraction. So which of these has the greatest electronegativity? That's going to be the one that is the hardest to pull. And you have to look at these. These are negatives, okay? So negative 51, that's the highest temperature. Negative 259 is the lowest temperature, somewhere in the middle. So we're looking for Hz. So Z is going to be the one that's the most polar bond, the greatest electronegativity, and the strongest bonding in between these molecules. 2, which of the following solids expect to have the highest melting point? Okay, so for ionic compounds, we're talking about Coulomb's law, and Coulomb's law is Q1, Q2 over D squared. So it's really the force equals K times negative, all that stuff. But it's charge and distance. So which of these is expected to have the highest melting point? It means the strongest interaction between them. Well, this magnesium is 2 plus 2 minus. This is 2 plus and 1 minus, 2 plus 2 minus, and 2 plus 1 minus. Okay, so I know it's probably my 2 plus 2 minus. And then the size, so the biggest charge, that's my Q1, Q2. Now I want the smallest size, because the smaller this denominator, the stronger the attraction. And magnesium is smaller than calcium. So this is my answer, magnesium, because if I have a small ion, positive, negative ion, then it's a small distance between those two. If I have larger ions, then it's a larger distance between those two. Okay, and it's not going to be as strong, so MgO. Okay, for the infrared spectrum for ethane, and ethine. Okay, well, we should recognize that we're talking about ethane. We're talking about a single bond between a couple of carbons. That looks terrible. Let me try one more time. Okay, we have a single bond between those carbons, so 1, 2, 3, 4, 5, 6. If I have ethene, I've got a double bond between those carbons, C2H4. And if I have ethine, then I've got a triple bond between those carbons, C2H2. So corresponds to the vibrations. The stronger the bond, okay, the more energy it's going to take for that vibration, higher energy. So if we have 39, 37, 35, okay, peak A is 39, so that's the strongest one, so that's my triple bond. The medium one's my double bond, the lower one's my single bond. So my peak A, B, and C correspond to ethine, ethene, ethane. Ethine, ethene, ethane. That's answer D. Okay, how many lone pairs are in the correct Lewis structure for xenon? Okay, so xenon difluoride. Xenon has 8 valence electrons. It takes 1 to hook on a fluorine, takes another 1 to hook on the other fluorine. Okay, that leaves 2 out of my 8, so I have 6 left, which is going to be 3 lone pairs, okay, on the central atom, and then I have lone pairs on the outer atoms. So how many lone pairs are in the correct Lewis structure? Looks like 9 lone pairs altogether. What's the bond order of the nitrogen-oxygen bond in the nitrite ion? Okay, well, nitrite, let's think about this. If I had N, I'm going to put N in the middle. If I had enough electrons, I would give everybody an octet. Okay, and that takes 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. But what do I have? I have 5 plus 6 plus 6. That's the nitrogen, oxygen, oxygen, plus 1 for that charge there. So that is 18 electrons, which means I'm going to end up with an extra electron. So my structure then, I can see, is going to be nitrogen, double bonded oxygen, single bonded oxygen, and a lone pair on the nitrogen. And I'm going to have a resonance structure for that, where I make a double bond to the left and a single bond to the right, and put in my lone pairs. And that's pretty sloppy. Okay, sorry about that. Okay, so what is the bond order? Okay, bond order for the nitrogen oxygen. This would be a bond order of 1. That's a bond order of 2. Okay, and we have to blend those together because later we say that's a 2 and a 1. And so what happens, it's going to be a 1.5 bond order, answer B. And that kind of always comes up. If there are 2 resonance structures, it's going to be 1.5. If there are 3 resonance structures, it's going to be 1.33. Okay, what's the formal charge on carbon and nitrogen in these cyanide ions, Cn-? Well, that assumes that you know how to draw cyanide, and if you work with it a little bit, you're going to come up with, I'm sorry, I forgot to do my brackets and charge on this other one, so just to be totally appropriate, let's do that. Okay, back here to cyanide. Okay, I have triple bond, lone pairs, because I have 10 electrons altogether, 4 for carbon, 5 for nitrogen, and 1 extra. And so say, what's the formal charge? On the carbon, you usually have 4 valence electrons. On nitrogen, you usually have 5. Okay, in this structure, I've got 1, 2, 3, 4, 5. And the nitrogen, same thing, 1, 2, 3, 4, 5. So on the nitrogen, I have a formal charge of 0. On the carbon, I have a formal charge of -1. Okay, so what is the formal charge on the carbon and nitrogen in the cyanide? So carbon -1, nitrogen 0. That looks like answer A. Number 7, which of the following molecules has the greatest bond angle, the largest bond angle? Well, that means we have to go through and draw these. Okay, so ClO2. Okay, I have Cl, I have O, and I have O. Okay, so what's going to happen? I'm going to start by giving everybody an octet. Okay, and ClO2, that's 7 plus 6 plus 6. Okay, that means I have too many, I don't have enough electrons, so I'm going to have to take back one of these. I'm going to make one of these into one big electron. Okay, so that's a steric number of 4. Okay, so it's going to be something like 109.5. Okay, it's going to be a little bit bigger because that was the guy's not going to, that single electron is not going to repel quite as much. Okay, CO2. CO2, we kind of how to have that one memorized because we see it all the time. It looks like this. Well, that's a bond angle of 180. Okay, I think that's definitely going to be my answer because how can I have anything bigger than that? Okay, NO2, we just did NO2, and we know NO2 is going to be like this. Okay, with a, I'm sorry, that was NO2 minus. Okay, this is just NO2. So on the central atom here, we're only going to have a single electron, not a pair of electrons. But still, that's going to be like a steric number of 3. It's going to be less than 180. And when I get to SO2, same situation, except SO2 is going to have a lone pair, full lone pair. So it's going to be more like 120. And again, it's going to have a resonance structure. So the biggest bond angle I'm going to have is the 180. So CO2 is my answer. Okay, which of the following is expected to be the most polar? Most polar, so we have some more drawing to do. And that's exactly the thing. There's a lot of drawing to do on all these. So carbon has 4 valence electrons. It's going to take 4 valence electrons to hook on our fluorines, put on the lone pairs. Okay, this is a very symmetrical molecule. This guy is not polar at all, so let's leave that off. SF4, okay, SF4, we can say, well, S has 6 valence electrons. It's going to take 4 of those to hook on our fluorines. That means we have 2 electrons left, so 1 pair on the central atom, and that's going to make this guy polar. That's going to be a seesaw shaped, so that's polar, so that's one of our possibilities. SiF4, well, SiF4 is exactly like carbon. You know, carbon, silicon, we're both in the same family. It's going to have the same structure, so that's not the answer. Okay, XeF4, well, XeF4, let's say Xe has 8 valence electrons. It's going to take 4 electrons just to hook on those fluorines, and that leaves us with 4 more electrons, and that's a steric number of 6 with 2 valence electrons. This guy's going to be square planar. Okay, and if it's square planar, if these are all in the same plane, it looks just like this, so it's going to be nonpolar. Any bond dipoles are going to cancel out. So the answer has to be answer B, SF4. Okay, a lone pair, one single lone pair on that central atom pretty much lets us know that's going to be polar. Okay, number 9, consider the following structural formula for caffeine. How many sigma and pi bonds? How many sigmas and pi's? Okay, that's not too bad. So if I'm going to do pi bonds, I'm going to have a double bond. So there's going to be a pi, there's going to be a pi, there's going to be a pi, there's going to be a pi. So I'm going to have 4 pi bonds. So I know my answer is either B or D. Now I have to count up my sigmas. Okay, well, every single bond is a sigma. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That's 25 sigma bonds. Now I said all the single bonds are sigmas, but and a double bond also has a sigma. So every bond, I should say, has a sigma. Now the 29, that is probably there to catch people who think that the lone pairs count as something. Okay, and that's just not true. Lone pairs don't do anything. They're not bonds, okay, so they don't count as sigmas or pi's. So 25 sigmas and 4 pi's. Number 10, a student would like to know the best absorbance to use for a colorimetry experiment to determine the concentration of pink cobalt chloride. Which type of spectroscopy is best to use? Okay, well, infrared, that is for molecular vibrations. Mass spectroscopy, that's not even close here. That's the kind we use for figuring out isotopes. Okay, X-ray, that was for figuring out the electron configurations. So it's UV vis, okay, ultraviolet visible light spectroscopy, and we use that for Beer's law in order to figure out the concentration of a colored chemical. Okay, and that's the answer. Okay, we get to the FRQs. Okay, so from 1999, answer the following questions. Draw the complete Lewis dot structure for CO2 and for carbonate. So CO2, like I said before, this is something I think you should have memorized because you just see it all the time. There's CO2. Okay, now carbonate, okay, when we do this, we're going to find out that there's going to be resonance where we're going to have to make a single bond and a double bond. That if we start off and give everybody an octet, then we find out that there's not enough electrons for that. So we're going to have CO3, C in the middle, O's around. And that double bond, we'd have to say we have 3 different places we could put it. So remember, a double bond gets 2 lone pairs, a single bond gets 3 lone pairs. And we can do it again with dots, or we can do it with lines, or we can do a combination of dots and lines. And each of these says 2 minus, and we should put double-headed arrows in between each one. Okay, so that's the complete Lewis dot structure for each species, and yes, you need to show all 3 resonance structures in order to get credit. Okay, account for the fact that the carbon-oxygen bond length in carbonate is greater than the carbon-oxygen bond length in CO2. Well, if we talked about bond order, okay, well, I'd say here in CO2, the bond order is 2. Okay, because I have 2 pairs of electrons holding those 2 atoms together. Here, I have 1, 2, 3, 4 bonds, okay, spread out over 3, different atoms. So it's 4 1/3. It's a 1.33 bond order. Which means in CO2, there are 2 pairs of electrons holding things together, whereas in carbonate, I only have 1 1/3 bonds holding those carbon and oxygens together. So the more electrons that are holding them together, the shorter that bond length is going to be. So more pairs of electrons equals shorter bond. And we could write that a little nicer, but that's the basic idea. Figure out the bond order. The more pairs of electrons you have holding things together, the shorter that bond's going to be. Okay, consider these molecules, CF4 and SF4. Draw the complete Lewis dot structures for these. Okay, so, oops, I should have gotten C over here first. Okay, carbon has 4 valence electrons. It's going to take 4 valence electrons to hook on those fluorines. Let's do the dots out here on the fluorines. Okay, sulfur has 6 valence electrons. It's going to take 4 of them to hook on the fluorines. And that means on the sulfur, I'm still going to have a pair of electrons left over. So you can see I'm going to have a steric number of 5, different things. In terms of molecular geometry, account for the fact CF4 is nonpolar, whereas SF4 is polar. Okay, that's pretty easy. Now we have to talk about both situations. Okay, so for CF4, it's tetrahedral. Okay, all the bond angles are 109.5. And all bond dipoles, okay, cancel. That's why it's nonpolar. Okay, for the other one here, for SF4, well, I have that lone pair. So what this is going to be steric number of 5, which is trigonal bipyramidal. So I have 1 up, 1 down, 3 around the middle, but one of those around the middle is a lone pair. So we can see what happens if I have a bond dipole this way and a bond dipole this way. They will cancel, but there's nobody to cancel these 2 bond dipoles that are sitting off one side. So 2 of those F have nothing to cancel it. So that is where the polarity of the molecule is going to come from. So because of this lone pair, where there's no atom there, there's nothing to cancel 2 of those bond dipoles, and that's why this molecule will be polar. Okay, for the next question, NO2, NO2 minus, and NO2 plus. Okay, so we have some drawing to do. Draw the Lewis dot structures for each of these. Now, we've drawn a couple of these already. So NO2 is going to have a single electron here. Okay, and that's going to have a resonance structure where we make a single bond to the right and double bond to the left. So that's sort of a steric number of 3. Okay, a little bit, the bond angle is a little bit large. Okay, NO2 minus, that's the same thing, only 1 more electron, which means this nitrogen then can have a pair of electrons, not a single electron. And that will resonate with the same thing here where I get single bonded O, double bonded O. Okay, and then if I have NO2 plus, that means I take away an electron. And if I take away electron, then I'm actually going to have the same number of electrons as if I had CO2. So it's going to look just like a CO2 molecule. And this will have a positive charge. These will both have negative charges. And I get resonance, resonance, and no resonance. So list of species in the order of increasing bond angle. Well, certainly the NO2 plus will have the greatest bond angle, 180 degrees. Okay, now these 2 are similar, except in one case I have a pair of electrons, in another case I have a single electron. So increasing bond angle, okay, so that single electron is going to be a little bit larger than if I have that double electron. So I would make this guy here, NO2, with a minus charge, my smallest bond. Okay, then I would have NO2, then I'd have NO2 plus. So certainly that's 180. These are somewhere like 120. Okay, but I say probably a little bit larger than 120 for this one. So maybe let's just guess and say 125. And let's say this is kind of like 120. They're guesses, but certainly a double bonded, a pair of electrons is going to reduce the size of my bond angle a little bit. Okay, select one of the species and give the hybridization of the nitrogen atom in it. Okay, well, it depends on which one you choose. Okay, so if we pick NO2, the first one, okay, then the NO2, and we have NO2 minus, and we have NO2 plus. Well, certainly this NO2 plus, that's easy. I would pick that one personally. And I would say the steric number is equal to 2. Okay, steric number of 2. That means this is sp hybridization. Okay, both of these others, you can see it's going to have a steric number of 3. So both of these are going to be sp2 hybridizations. Even if it only has 1 electron, we still count that as a steric number of, 2 bonded atoms, 1 lone pair. That 1 alone electron still counts. So steric number 3, steric number 3, steric number 2, sp2, sp2, and sp. Identify the only species that dimerizes and explain why that happens. It's this guy. And what happens if we have a nitrogen that has a single electron, that single electron can bond with a single electron on another one of these molecules. And the question comes up, what do we mean by dimer? Di means 2, mer means parts. Okay, so 2 parts going together, so they would make a bond. So those single electrons bond together to make a nice single bond between those. And I think there would be resonance structures where you have the double bonds, single bonds for the N's and O's. But that's basically, this is the N2O4 molecule. And we saw that when we did our demonstration for Le Chatelier. where we had the reddish-brown smog, NO2, and then we put it into dry ice and it lost its color, and it turned into the colorless N2O4. And that's a dimer. And I think that's the end of the test. Okay, good luck.